There's something hauntingly beautiful about the NGC 262 galaxy, a swirling tapestry of stars and cosmic dust shimmering in the vast emptiness of space. But behind its serene glow lies a secret. This galaxy is a hotbed of the unexplained, a place where the laws of physics seem to twist and bend in ways that leave even the most brilliant scientists baffled. Imagine a region of the universe where stars vanish without a trace, where mysterious energy surges flicker like ghostly signals, and where dark matter behaves in ways no one can predict. This isn't science fiction, it's the reality of NGC 262, a cosmic enigma that challenges everything we think we know about how the universe works. What makes this galaxy so unusual? For starters, it's home to at least 30 documented phenomena that defy logic, events so strange they've sparked debates among astronomers for decades. Some believe these anomalies could rewrite our understanding of space itself, while others wonder if we're glimpsing something far more profound, a hidden layer of reality just beyond our grasp. From unexplained radio pulses that echo like cosmic whispers to bizarre gravitational distortions that warp the very fabric of space-time, NGC 262 is a treasure trove of mysteries waiting to be unraveled. And that's exactly what we're going to do. Over the course of this journey, we'll dive deep into the most mind-bending phenomena lurking within this galaxy, piece by fascinating piece. You'll witness celestial oddities that seem ripped straight from the pages of a thriller, objects that shouldn't exist, forces that shouldn't behave this way, and clues that hint at something even bigger lurking in the shadows of the cosmos. So settle in, because by the time we're done, you'll never look at the night sky the same way again. The universe is stranger than we ever imagined, and NGC 262 is proof. One of the most unsettling mysteries within NGC 262 is what astronomers have dubbed the phantom black hole, a cosmic anomaly that flickers in and out of existence like a ghost in the machinery of the universe. Unlike typical black holes, which anchor themselves firmly in space, this one vanishes without warning, leaving behind no detectable trace. One moment, telescopes pick up the unmistakable gravitational pull and X-ray emissions of a massive black hole. The next, nothing, just empty space where a celestial monster should be. Theories about what's causing this bizarre behavior range from the mind-bending to the downright revolutionary. Some scientists suggest we might be witnessing an extreme case of gravitational lensing, where the warped spacetime around another massive object bends light so severely that it creates a temporary, illusionary black hole. Picture a funhouse mirror on a cosmic scale, distorting reality just enough to trick our instruments into seeing something that isn't truly there. Others propose something far stranger, that this black hole could be interacting with exotic forms of matter we've never directly observed. Hypothetical particles like dark matter or even theoretical quintessence fields might be altering its behavior in ways that defy our current understanding of physics. Imagine pouring invisible ink into water. It changes the properties of the liquid without leaving a visible trace. Could something similar be happening here, with unseen forces nudging this black hole in and out of our observable reality? Then there's the most radical idea of all, that this black hole isn't entirely in our universe. Some theorists speculate it might exist at the edge of a hidden dimension, briefly intersecting with our own before slipping back into the cosmic shadows. It's a concept straight out of science fiction, but in NGC 262, fiction and reality seem to blur. What's certain is that the phantom black hole defies every textbook explanation. Its existence, or rather, its intermittent existence, challenges the very definition of what a black hole can be. And if one thing's clear from studying NGC 262 other oddities, this won't be the last time this galaxy forces us to rethink our place in the cosmos. If the phantom black hole left you questioning reality, wait until you hear about the next enigma lurking in NGC 262, the ghostly radio echo. This isn't just any cosmic signal. It's a series of repeating radio bursts that pulse with such precise, almost rhythmic regularity. They've sparked debates about whether we're listening to the heartbeat of a dying star, or something far more intentional. Unlike the chaotic radio noise typically emitted by celestial objects, these signals arrive in patterns so distinct they've been compared to Morse code transmissions from deep space. At first, astronomers assumed they'd stumbled upon a new type of pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. But pulsars have a predictable decay, their signals slowing over time as they lose energy. These echoes, they don't fade. They repeat with clockwork consistency, sometimes vanishing for years before reappearing unchanged, as if something or someone flicked a cosmic switch back on. Theories trying to explain these signals swing from the scientifically plausible to the wildly speculative. One camp argues they could be the result of a rare celestial collision, like two ultra-dense neutron stars locking into a bizarre orbital dance, their magnetic fields twisting into a natural transmitter. Picture two hyperactive magnets spinning around each other, generating radio waves like a cosmic generator. Then there's the more unsettling possibility: what if these signals aren't natural at all? The patterns are just a little too uniform, a little too deliberate. Some researchers cautiously point to the infamous WOW signal of 1977, a one-off radio burst that still hasn't been explained. Could this be its more persistent cousin? The idea of an extraterrestrial origin is tantalizing, but here's the catch: NGC 262 is over 100 million light-years away. Any civilization capable of broadcasting signals that far would need technology beyond our wildest dreams. Yet the most fascinating hypothesis doesn't involve aliens at all. A handful of physicists propose these echoes might be evidence of cosmic strings, theoretical defects in space-time left over from the birth of the universe. If these strings vibrate like guitar strings, they could produce radio waves in predictable bursts, a relic of the universe's infancy echoing across the eons. What makes the ghostly radio echo so compelling isn't just the mystery of its origin, it's the way it forces us to confront how little we truly understand about the cosmos. Whether it's a natural phenomenon we've yet to decipher or something more extraordinary, one thing's clear: NGC 262 isn't just showing us the universe's secrets. It's whispering them one cryptic pulse at a time. Just when you thought NGC 262 couldn't get any stranger, there's the case of the vanishing star cluster, an entire group of stars that blinked out of existence in what amounts to a cosmic heartbeat. Astronomers first documented this cluster over a decade ago, a glittering jewel box of young, massive stars burning brightly near the galaxy's core. Then, between one observation and the next, they were gone. Not dimmed, not scattered, just vanished as if someone had flipped off a light switch in the depths of space, the most straightforward explanation. A sudden, catastrophic collapse into a black hole. Normally, stars die in spectacular supernova or slowly fade over eons. But under extreme conditions like a cluster packed too tightly, gravity could theoretically win all at once, triggering a chain reaction where stars plummet into a central point, birthing a supermassive black hole in a single, violent instant. Picture a crowd surging toward an exit so rapidly that the crush itself becomes the disaster. If this happened here, it would be the fastest such event ever recorded, rewriting our understanding of stellar life cycles. But there's a problem with that theory. Even the most rapid black hole formation should leave behind some trace, a burst of gamma rays, a ripple in space-time, something. Yet telescopes detected nothing, no energy spike, no debris field, just silence where a cosmic catastrophe should have echoed. That absence has led to more speculative ideas, including one that taps into the Fermi paradox. the unsettling question of why, in a universe teeming with stars, we've found no evidence of other civilizations. Some researchers wonder if the cluster's disappearance could point to activity on a scale beyond natural phenomena, like a Dyson sphere network, hypothetical megastructures built by advanced civilizations to harness a star's energy. If an entire cluster were enclosed this way, the star's light would vanish from our view, leaving only infrared heat signatures. Yet even this theory falters. No such heat spike was detected either. Perhaps the most unnerving possibility is that we're seeing the footprint of something even more exotic. Could dark energy, the mysterious force accelerating the universe's expansion, have localized effects, tearing structures apart faster than light can carry the evidence to us? Or does NGC 262 harbor a flaw in spacetime itself, a cosmic trapdoor where matter occasionally slips into oblivion? Whatever the truth, the vanishing star cluster forces us to confront how little we know about the rules or the exceptions governing the cosmos. In a universe where stars can disappear without a whisper, even the most solid laws of physics start to feel like guidelines, written in pencil. Deep within the swirling dust clouds of NGC 262, scientists have stumbled upon something that shouldn't be possible, a phenomenon they're calling the quantum ripple effect. Here, particles don't behave like they're supposed to. Instead of moving smoothly through space, they seem to vanish from one spot and reappear a short distance away, as if the universe itself has developed a glitch. It's not quite teleportation, but it's close enough to make physicists question whether we've missed a fundamental rule of reality. What makes this so baffling is that these quantum jumps aren't random. They follow a peculiar pattern, almost like stones skipping across a pond, leaving behind faint traces of energy that defy conventional explanations. Under normal circumstances, particles might tunnel through barriers at the subatomic level, a well-documented quantum quirk, but this is different. The distances are larger, the energy signatures stranger. It's as if the fabric of spacetime in NGC 262 is thinner or maybe frothier. That's where the idea of spacetime foam comes in. First proposed by theoretical physicist John Wheeler back in the 1950s, the concept suggests that at the smallest scales, spacetime isn't smooth. Instead, it's a bubbling, turbulent sea of tiny fluctuations like the surface of a boiling pot viewed under a microscope. In most of the universe, these fluctuations are too minuscule to notice. But in NGC 262 dust clouds, something might be amplifying them, creating pockets where particles slip through the foam like marbles rolling through a sieve. Could this be our first glimpse of quantum gravity in action? Einstein's theory of general relativity works beautifully on cosmic scales, while quantum mechanics rules the subatomic world. But the two frameworks refuse to merge neatly, leaving a gap in our understanding of how gravity operates at the tiniest levels. If these ripples in NGC 262 are evidence of quantum gravity, where spacetime itself becomes granular, it would be a breakthrough decades in the making. Not everyone's convinced, of course. Skeptics argue these observations could stem from exotic magnetic fields warping particle paths, or even undiscovered types of dark matter interacting with the dust. But the most compelling data points to something more profound. When researchers simulated conditions resembling spacetime foam, the predicted particle behavior eerily matched what's being observed. It's still speculative, but the pieces fit a little too well to ignore. What's truly mind-bending is the implication. If spacetime can fray or ripple this way in NGC 262, could it happen elsewhere? Are we looking at a universal phenomenon that's just more visible here, or is this galaxy somehow special? The answers might rewrite not just our understanding of gravity, but the very nature of reality itself. And if there's one lesson NGC 262 keeps teaching us, it's that the universe is far stranger, far more dynamic than we ever dared to imagine. In the bustling stellar neighborhood of NGC 262, astronomers witnessed something that defied every expectation, a supernova that refused to rush. While most of these stellar explosions blaze brilliantly for mere weeks before fading, one particular event stretched across decades, unfolding in agonizingly slow motion like a cosmic film stuck on pause. Dubbed the time-dilated supernova, this anomaly didn't just puzzle scientists, it threatened to upend our understanding of how stars die. At first, researchers assumed it was a trick of perspective. Perhaps light from the explosion was taking a detour around a massive object, warped by gravity in a phenomenon called lensing. But calculations ruled that out. The supernova's light wasn't being bent. Time itself seemed to stretch around it. Imagine watching a firework explode in midair, only for its sparks to hang frozen for years, their glow lingering far longer than physics allows. That's the enigma astronomers faced. The leading theory points to dark energy, the mysterious force accelerating the universe's expansion. Normally, dark energy works on cosmic scales, gently pushing galaxies apart. But what if it could act locally, too? Some speculate this supernova might have erupted in a pocket of space where dark energy's influence is unusually strong, creating a kind of temporal quicks, and that slowed the explosion's progress. Picture a runner trying to sprint through honey. Every movement becomes sluggish, every action delayed. If true, this would be the first direct evidence of dark energy interacting with individual stellar events, a revelation that could reshape cosmology. Then there's the wildcard possibility, a collision with exotic matter. Certain hypothetical particles like cue balls or strangelets could theoretically alter the fundamental forces governing supernova, stretching their death throes into a drawn-out spectacle. It's a fringe idea, but in a galaxy as peculiar as NGC 262, fringe ideas often become front-runners. But the most tantalizing clue lies in the supernova's light curve, the graph tracking its brightness over time. Instead of the sharp peak and gradual fade seen in normal supernova, this one plateaued for years, as if something were artificially stoking the flames. One radical paper suggests the star might have been encased in a thick shell of previously ejected material, creating a cosmic echo chamber where light bounced around before escaping. Others wonder if we're seeing the aftermath of a star so massive. Its core collapse triggered a cascade of lesser explosions, like a series of tremors following an earthquake. Whatever the cause, the time-dilated supernova forces us to confront how much we still don't know about the universe's most violent events. If stars can die in slow motion here, what other rules might NGC 262 bend or break? Every anomaly in this galaxy feels like a puzzle piece to a bigger picture, one where the cosmos plays by its own hidden rules. And with each discovery, we're left grappling with a humbling truth. The universe is far stranger, far more inventive than our textbooks ever suggested. Among the swirling cosmic clouds of NGC 262, there's a structure so eerily precise, it looks as if it were crafted rather than born. The Mirror Nebula doesn't just scatter light, it throws it back with near mathematical symmetry, like a vast, polished sheet of cosmic glass floating in the void. Most nebulae are chaotic, their glow diffused by turbulent dust and gas. But this is different. Its reflections are crisp, its edges unnervingly sharp, as if someone or something took a celestial brushstroke and painted perfection across the darkness. At first glance, you might mistake it for a known reflective nebula, like the Witch Head Nebula in Orion, where starlight bounces off dust particles like sunlight on snow. But those natural mirrors are messy, their glow uneven and speckled. The Mirror Nebula, by contrast, behaves more like a literal mirror. Its surface so uniform, it creates near-flawless duplicates of stars behind it, their images warped only by the subtlest curvature. It's as if space itself folded here, creating a pocket of impossible geometry. Astronomers are torn between awe and unease. The the leading theory suggests an ultra-dense shell of metallic dust forged in the heart of a long-dead star might have settled into a perfectly smooth layer. Picture a frozen lake so still it reflects the mountains without a ripple, but even that explanation feels inadequate. Natural processes rarely produce such precision, especially on this scale. The nebula spans light years, yet its surface varies by less than a fraction of a percent in density. That's like stretching a sheet of aluminum foil across an entire continent and finding not a single wrinkle. Then there's the fringe hypothesis, the one that sends a shiver down the spine. Could this be evidence of cosmic engineering? Structures like Dyson spheres or alien megaprojects have long been theorized, but always as constructs around stars, not free-floating mirrors adrift in space. Yet the nebula's behavior fits unsettlingly well with speculative designs for solar sails or energy collectors, devices meant to harness or redirect light on an unimaginable scale. Of course, Occam's razor favors natural explanations, and some researchers propose a middle ground. Perhaps the nebula's symmetry stems from a rare magnetic field alignment, locking particles into a grid-like formation. Or maybe we're witnessing the aftermath of a hypernova, whose shockwave sculpted the surrounding gas with unnatural neatness, like a blast wave frozen in time. But the most tantalizing clue lies in the nebula's heart. Deep within its shimmering layers, telescopes have detected rhythmic pulses of infrared light, tiny, regular bursts with no obvious source. They're too faint to be stars, too steady to be random. If nature abhors a vacuum, it despises perfect order even more, and that's what makes the Mirror Nebula so haunting. In a universe built on chaos, it stands as a quiet defiance, a cosmic anomaly that refuses to blur. Whether it's a masterpiece of physics or something beyond, one thing's certain: NGC 262 has a way of turning our assumptions into dust. In the heart of NGC 262, there's a place where the universe seems to forget its own rules. A sprawling region astronomers call the gravity anomaly. Here, the familiar tug of gravity doesn't just weaken or strengthen. It twists, objects speed up without visible force, drifting through space as if pushed by invisible hands. Stars zigzag like skaters on frictionless ice, their trajectories defying every known law of motion. It's as if Newton's apple, instead of falling, had suddenly shot sideways into the sky. What could possibly cause such chaos? The leading theory points to dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Normally, dark matter's gravity binds galaxies together, acting as cosmic glue. But in this pocket of NGC 262, it might be clumping in bizarre, unstable formations, creating gravitational hotspots that pull and push in unpredictable ways. Picture a magnet buried in sand, its unseen force tugging metal scraps erratically from below. Now imagine that magnet is made of something even stranger, hypothetical negative mass. That's where the science veers into the extraordinary. Negative mass, a concept straight out of theoretical physics, wouldn't just resist gravity, it would repel it, generating anti-gravitational effects. If such matter exists here, even in trace amounts, it could explain the anomaly's erratic behavior. Objects might accelerate toward positive mass while being shoved away by negative mass, caught in a cosmic tug-of-war. It's a wild idea, but in a galaxy where stars vanish and black holes flicker, wild ideas start to feel plausible. Yet there's another, even more unsettling possibility, that we're seeing the fingerprints of a higher dimension. Some models of string theory suggest gravity could leak between dimensions, weakening or distorting in our observable universe. If NGC 262 sits near a fold in spacetime's fabric, the gravity we detect might only be a fraction of what's truly there, like hearing an echo of a scream from another room. The implications are staggering. If gravity can bend this way, entire chapters of astrophysics might need rewriting. orbits, galactic formation, even the fate of the universe itself could look different under this lens. And while skeptics argue these observations might stem from hidden black holes or rogue planets, one haunting fact remains: the anomalies' effects are too widespread, too coordinated to be random. Whatever's lurking in this corner of NGC 262, it's not playing by the rules, and that's the most thrilling and terrifying part of all. Tucked away in the outer reaches of NGC 262, astronomers have detected something that shouldn't exist: a faint, razor-straight scar slicing through the fabric of space itself. This isn't a chance alignment of stars or a trick of perspective. It's a potential cosmic string, a hypothetical crack in the universe's foundation so dense, a single mile of it could outweigh Earth. If confirmed, it would be the first real evidence of these elusive space-time defects predicted by theory but never seen until now. What exactly is a cosmic string? Picture the universe in its infancy, a seething cauldron of energy cooling into the cosmos we know today. As space transitioned, theorists argue flaws could have formed like cracks in ice as it freezes. These wouldn't be made of matter, but of pure space-time curvature, thinner than an atom yet impossibly heavy, stretching across galaxies with gravitational ferocity. Think of them as cosmic fault lines where the rules of physics strain under tension. In NGC 262, the string's presence would explain two enduring mysteries: the galaxy's bizarre, warped shape and the torrents of high-energy radiation pouring from seemingly empty space. Normally, galaxies flatten into orderly spirals under gravity's pull, but NGC 262 looks like it's been twisted by an invisible hand, its arms kinked at unnatural angles. A cosmic string's gravity could do just that, warping the galaxy like a wire bending a sheet of foil. Meanwhile, the string's mind-bending physics might also generate the galaxy's unexplained energy bursts. As these space-time defects vibrate or snap, they could release shock waves of gravitational energy, sparking particle collisions intense enough to mimic the birth of stars. But the most tantalizing clue lies in the light from distant quasars behind NGC 262. Some beams appear duplicated, as if passing through a lens, except there's no massive object to bend them. A cosmic string's extreme gravity could split light like a prism, creating double images without the need for dark matter or black holes. It's a signature so distinct, researchers call it the fingerprint of these space-time scars. Not everyone's convinced, of course. Critics point out that similar distortions could stem from rogue dark matter clumps or even a chance alignment of unseen black holes. But the sheer straightness of this anomaly defies random chance. Nature loves curves and chaos, a perfect linear defect spanning light years that's harder to dismiss. If this truly is a cosmic string, the implications are staggering. These relics from the universe's first moments could be threads woven through all of space, a hidden web shaping the cosmos in ways we're only beginning to imagine. They might even hold clues to the universe's ultimate fate, whether it will expand forever, collapse, or tear itself apart along these very flaws. For now, NGC 262 cryptic signature remains a riddle. But one thing's certain: in a galaxy already overflowing with enigmas, this might be the most profound of all. Buried in the depths of NGC 262, there's a star that refuses to die, a cosmic Methuselah shining defiantly against the relentless march of time. Most stars of its size should have burned out billions of years ago, collapsing into white dwarfs or exploding in supernovae. But this one, it flickers on, stubbornly persisting like a candle that somehow never melts. Astronomers call it the immortal star, and its existence throws every model of stellar evolution into question. What makes this star so baffling isn't just its age, it's the way it behaves. Spectral analysis reveals an atmosphere brimming with elements that shouldn't exist in a star this old, like lithium and beryllium, metals typically consumed in a star's fiery youth. It's as if this ancient giant has a secret fountain of youth, replenishing itself against all odds. The leading theory: we might be looking at a relic from the universe's dawn, a rare population 3 star, a hypothetical first generation of stars forged from pure hydrogen and helium left over from the Big Bang. These primordial titans were thought to have died out eons ago, their short, violent lives ending in explosions that seeded the cosmos with heavier elements. But if one survived, hidden in NGC 262, it would rewrite our understanding of stellar archaeology. Then there's the more radical possibility. This star isn't just old, it's cheating death through exotic physics. Some researchers speculate its core might have transitioned into an entirely new state of matter, where protons and neutrons break down into a soup of quarks. In normal stars, fusion stops when elements like iron pile up, choking the core. But in quark fusion, even iron could theoretically be crushed into quark-gluon plasma, releasing staggering amounts of energy. Picture a car running on gasoline long after the tank should be empty, only to switch seamlessly to rocket fuel. If quark fusion is real, it could explain the immortal star's longevity and hint at an entirely unknown stellar life cycle. Not everyone's convinced, of course. Skeptics argue the star might simply be a cosmic imposter, a younger star that wandered into NGC 262 after a galactic collision, its odd composition a result of cannibalizing older neighbors. Others propose a more unsettling idea, that we're witnessing the work of dark matter. Certain theoretical particles could accumulate in a star's core, annihilating quietly and providing a slow, steady energy source. It's like a stellar battery charged by the invisible scaffolding of the universe itself. But the most tantalizing clue lies in the star's heartbeat, like pulsations. Most aging stars fluctuate predictably as their fuel wanes, but this one thrums with eerie regularity, as if something beneath its surface is orchestrating its survival. Whether it's a fossil from the cosmos' infancy or a laboratory for bizarre physics, the immortal star forces us to confront how much we still don't know about the lives and afterlives of the universe's brightest giants. In a galaxy already brimming with anomalies, this one doesn't just defy expectations, it mocks them. If you thought storms were just a weather phenomenon, NGC 262 has a cosmic surprise in store, a hurricane unlike any other, made not of wind and rain, but of the universe's most mysterious substance, dark matter. Telescopes first detected this invisible tempest through subtle distortions in starlight, the telltale signature of gravitational lensing. But instead of the gentle warping caused by ordinary matter, this lensing effect twisted and writhed, revealing a vast, swirling vortex tearing through the galaxy's outskirts. Imagine a hurricane so massive it could engulf entire star systems, only you can't see it because it's built from the very fabric that holds the cosmos together. The sheer scale of this dark matter storm is staggering. Stretching across thousands of light years, its gravitational currents are powerful enough to nudge stars off course, sending them drifting like ships caught in a rogue wave. Some researchers compare it to the Milky Way's own dark matter river, a stream of invisible particles detected near our solar system. But NGC 262 version is far more violent, a maelstrom of unseen forces churning with enough energy to reshape entire clusters of stars. The question is, what could unleash such chaos? One theory points to a catastrophic collision in the galaxy's past. When two galaxies merge, their dark matter halos can slosh together like invisible tidal waves, creating turbulent eddies that linger for billions of years. Picture pouring cream into coffee. The swirls don't vanish instantly. They spiral and twist before finally blending. If NGC 262 once devoured a smaller neighbor, the aftermath might explain this enduring storm. Simulations show such mergers could leave behind dark matter weather systems, chaotic remnants that persist long after the stars have settled. But there's a darker possibility. What if this hurricane isn't a relic at all, but something actively fed by an unseen force? Some models suggest that certain types of dark matter, like hypothetical, self-interacting particles, could clump and flow like liquid, forming structures that behave in ways ordinary matter can't. In this scenario, the storm might be funneling dark matter toward the galaxy's core, fueling something even more bizarre lurking in the shadows. The real mystery, though, is how this invisible tempest affects everything around it. Stars near its path show odd, erratic orbits as if tugged by unseen currents. One particularly eerie discovery, a planetary system where the outer worlds orbit at unnatural angles, their paths tilted as though twisted by a giant hand. Could this be dark matter's fingerprint, a hidden force sculpting systems in ways we're only beginning to detect? Then there's the most unsettling implication. If dark matter can gather into storms, what else might it form? Galaxies are thought to be embedded in vast halos of the stuff, but if it's capable of this level of organization, could there be entire dark matter structures, rivers, mountains, even cities woven into the fabric of space, invisible to our eyes but shaping the universe all the same? NGC 262 Hurricane might just be the first clue to a hidden cosmic geography, one we're only starting to map, and in a galaxy already overflowing with enigmas, that's a revelation that changes everything. Among the swirling cosmic wonders of NGC 262, there exists a silence so profound it defies physics, a place astronomers call the electromagnetic void. Here, radio waves, X-rays, even visible light enter but never return, as if the galaxy itself has a hidden drain swallowing every photon whole. Unlike black holes which devour light with observable fury, this region absorbs without a trace, no bursts of radiation, no swirling accretion disks, just an eerie absence where signals go to die. At first, scientists suspected an extreme version of known absorption mechanisms. Dense molecular clouds, for example, can block certain wavelengths, but they scatter as much as they absorb, creating telltale shadows in telescopic data. The void leaves no such fingerprints. It's more like a room where sound vanishes the moment it's made. No echo, no distortion, just nothing, even more puzzling. The effect isn't consistent. Some frequencies vanish entirely, while others pass through unscathed, as if the void is selectively erasing only parts of the electromagnetic spectrum. This selective silencing has sparked radical theories. One suggests we're observing a knot in space-time where extra dimensions leak into our own. In certain string theory models, gravity isn't the only force that might bleed between dimensions. Electromagnetic waves could slip through microscopic cracks in reality's fabric, vanishing into realms we can't perceive. Picture a radio playing in a sealed room, its sound muffled not by walls, but by the very air thinning into another universe. Then there's the darker possibility, a collision with an anti-photon field. Hypothetical particles called shadow photons, invisible counterparts to normal light, could theoretically cancel out electromagnetic waves on contact, like matter and antimatter annihilating one another. If such a field drifts through NGC 262, it might explain the void's surgical precision, silencing specific wavelengths while leaving others untouched. But the most haunting idea comes from quantum physics. What if the void isn't absorbing light at all, but slowing it to a standstill? In lab experiments, scientists have frozen light mid-pulse using ultra-cold gases. Scale that up to cosmic proportions, and you might get a region where photons stall indefinitely, trapped in a strange quantum limbo. The light wouldn't vanish, it would simply stop moving, stretching seconds into eternity. Whatever the truth, the electromagnetic void forces us to confront the limits of our cosmic maps. In a universe brimming with invisible dark matter and hidden dimensions, even empty space might be hiding secrets we've only begun to glimpse. And if one patch of NGC 262 can silence light itself, what other rules might it bend or break when we're not looking? Hidden among the fiery swirls of NGC 262, something glows with an eerie, almost living light. vast clouds of gas pulsing with bioluminescent hues, their colors shifting like the auroras of an alien world. These aren't the usual emission nebulae, where ultraviolet radiation from nearby stars excites atoms into a predictable palette of reds and blues. These clouds flicker with organic greens, deep purples, and even fleeting streaks of gold, as if the galaxy itself is breathing. It's a spectacle so reminiscent of Earth's deepest oceans, where creatures wield light like a language that scientists can't help but wonder, is this just a dazzling chemical fluke, or could we be staring at something far more extraordinary? The chemistry behind these clouds is strange enough on its own. Normally, nebular gases glow when electrons, knocked loose by stellar radiation, recombine with atoms, a process that emits specific wavelengths depending on the elements present. Oxygen burns red, hydrogen shimmers pink, but these clouds, their spectra defy easy categorization. They emit light at wavelengths that shouldn't exist in sterile interstellar space, matching patterns seen in rare microbial fluorescence or even the cryptic flashes of deep-sea jellyfish. One theory suggests an exotic cocktail of metals like iridium or europium might be interacting with cosmic rays in ways we've never observed, creating a natural light show. Picture a neon sign powered not by electricity, but by the raw chaos of space itself. Yet there's a more tantalizing, if controversial, idea lurking in the data. What if this luminosity isn't purely chemical? On Earth, bioluminescence serves a purpose: communication, camouflage, attraction. Could these clouds, in some unimaginable way, be doing the same? The notion of cosmic scale life isn't new. Astronomers like Fred Hoyle once speculated about organic nebulae, vast entities metabolizing starlight and evolving over eons. While mainstream science dismisses this as fantasy, NGC 262 glowing clouds revive the debate. Their light patterns aren't entirely random. Some regions pulse in slow, rhythmic cycles, while others flare in response to passing shockwaves, almost like a reflex. Skeptics, of course, have counter-arguments. Complex organic molecules like polycyclic aromatic hydrocarbons are known to exist in space and could produce similar emissions under extreme conditions. Others point to magnetized plasma vortices, twisting magnetic fields that might accelerate particles into unnatural energy states. But the most compelling counterpoint is also the simplest. Life as we know it requires liquid solvents and molecular complexity, things these diffuse clouds seemingly lack. Then again, as we know it might be the key flaw in that logic. If there's one lesson NGC 262 keeps teaching us, it's that the universe thrives on shattering assumptions. Whether these clouds are a chemical curiosity or something more profound, their very existence forces us to stretch our definitions of what's possible. After all, in a galaxy where black holes flicker and stars defy death, why couldn't light itself become a living thing? The answer, much like those shimmering gases, remains just out of reach, glowing, shifting, and daring us to look closer. Imagine a world without a sun, no golden sunrise, no setting dusk, just endless night stretching into eternity. Yet somehow, against all odds, these planets aren't frozen wastelands. They're cosmic nomads drifting through the void of NGC 262 with temperatures stable enough to sustain liquid water, as if nature itself forgot to read the rulebook. These are the paradox planets, and their existence throws every textbook on planetary formation into chaos. Normally, rogue planets, worlds untethered from any star, should be inhospitable ice balls, their surfaces plunging near absolute zero without a nearby sun to warm them. But in NGC 262, telescopes have detected at least a dozen of these lone wanderers emitting faint, steady heat signatures. Some even show atmospheric chemistry suggesting balmy conditions, with water vapor and organic compounds swirling in their skies. It's like finding a campfire burning in the middle of an Arctic storm, with no one around to tend the flames. So how is this possible? One leading theory points to hidden brown dwarfs, failed stars too dim to detect with current technology. These cosmic embers, though not massive enough to ignite full fusion, could still smolder for eons, radiating just enough heat to warm nearby planets. Picture a flashlight buried under thick blankets. The glow might be invisible from a distance, but it could still keep your hands warm. If NGC 262 is littered with these stealthy brown dwarfs, they might explain the paradox planet's mysterious warmth. But there's a catch. Brown dwarfs should leave gravitational footprints, subtly tugging on surrounding objects. Yet these rogue worlds drift with eerie smoothness, their paths undisturbed. That absence has spurred wilder ideas, like planets heated from within by exotic energy sources. On Earth, radioactive decay and tidal forces from our molten core generate internal heat. But the paradox planets would need something far more potent, perhaps interactions with dark matter, where hypothetical particles collide and release energy as they annihilate in a planet's core. It's a stretch, but in a galaxy where dark matter forms hurricanes, why couldn't it also play furnace? Then there's the most mind-bending possibility, that these planets aren't orphans at all, but refugees from a catastrophic stellar breakup. When binary stars violently separate, their planets can be flung into the void, carrying the thermal echoes of their former suns like embers in a dying fire. Simulations show such worlds could retain heat for billions of years, their thick atmospheres acting like cosmic insulation blankets. But the real enigma isn't just how these planets stay warm, it's what their existence implies about the universe's hidden habitats. If life can arise near stars, why not here? Beneath the ice shells of these wandering worlds, subterranean oceans might churn, heated by geothermal vents or dark matter reactions. In the endless night of interstellar space, the paradox planets could be silent arcs, carrying the seeds of life far from the glare of any sun. NGC 262 rogue worlds force us to rethink the very definition of a habitable zone. Maybe the universe is far more generous and far stranger than we ever imagined, and if planets can thrive without stars, how many more cosmic miracles are waiting unseen in the dark? At the heart of NGC 262, buried beneath swirling layers of cosmic dust and ancient starlight, lies an object so impossibly dense it shouldn't exist: the crystal core. Unlike the chaotic neutron stars we're familiar with, spinning frenzied corpses of collapsed suns, this structure pulses with eerie regularity, its light not flickering but ringing like a struck tuning fork. Telescopes have detected something even more bizarre. Its surface isn't a turbulent sea of crushed atoms, but a near-perfect lattice, as if the entire star froze mid-spin into a cosmic diamond. Neutron stars, the remnants of supernova explosions, are supposed to be messy. Their cores are a soup of hyper-compressed neutrons, while their surfaces churn with magnetic storms powerful enough to rip molecules apart from light years away. But the crystal core breaks every rule. Spectroscopy reveals sharp, clean emission lines, signatures of atoms aligned in orderly rows, like soldiers standing at attention. It's as if someone took the heart of a star and forged it into a flawless gem the size of Manhattan. This level of symmetry defies conventional physics. Under the insane pressures inside neutron stars, matter should collapse into quantum chaos, not arrange itself into crystalline perfection. That's why some theorists suspect we're not looking at a neutron star at all, but something far rarer, a quark star. In this hypothetical object, the crushing gravity would be so intense that even neutrons break apart, their constituent quarks spilling out to form a new state of matter, one that could theoretically settle into stable, lattice-like structures. Picture a snowflake forming in a blizzard, but instead of water molecules, it's built from the fundamental building blocks of reality itself. Even quark stars shouldn't be this orderly, though. That's where the mystery deepens. One radical paper suggests the core might be threaded with strange quarks, an exotic variety that could stabilize the lattice against collapse. Another posits that it's not a natural object at all, but the relic of an ancient civilization's attempt to harness stellar energy, a wild idea. But in a galaxy where light pulses like Morse code and nebulae reflect like mirrors, even the wildest ideas start to feel plausible. The most compelling clue lies in the core's vibrations. When neutron stars quake, they release bursts of radiation like cosmic screams. The crystal core, though, hums. Its oscillations produce harmonic frequencies, as if the entire structure were resonating like a bell. If confirmed, this could be the first direct evidence of a quantum phase transition in stellar-scale matter, a discovery that would rewrite textbooks on particle physics and stellar evolution alike. What's clear is this: the crystal core doesn't just challenge our understanding of stars, it taunts it. In a universe where matter is supposed to crumble under pressure, NGC 262 Gleaming Heart stands as a defiant counterpoint, a cosmic rebel that chose against all odds to turn chaos into order. Whether it's a natural marvel or something beyond our current science, one thing's certain: the rules here aren't just being bent, they're being rewritten. Deep within NGC 262 tangled web of stars, astronomers have stumbled upon a celestial soloist, a magnetar that doesn't just pulse with deadly radiation but sings. Dubbed the singing magnetar, this ultra-dense stellar corpse vibrates with eerie precision, its oscillations spiraling outward as harmonic frequencies so mathematically pure they've been compared to the chiming of a cosmic bell. Most magnetars are known for their violent tantrums, bursts of X-rays and gamma radiation powerful enough to strip planets clean of their atmospheres from halfway across the galaxy. But this one, it's composing symphonies in space-time itself. What makes this magnetar's song so extraordinary isn't just its beauty, it's the physics behind the music. When massive stars collapse, their cores can spin rapidly, wrapping magnetic fields so tightly they become 1 trillion times stronger than Earth's. Normally, these magnetic monsters quake and fracture under the strain, releasing energy like a snapped rubber band. The singing magnetar, however, trembles with near-perfect periodicity, as if its entire structure were resonating like a finely tuned instrument. Picture plucking a guitar string and hearing the same note hold for years without fading. That's the level of stability we're talking about. Scientists believe these vibrations might be glimpses of starquakes on an unimaginable scale. Just as earthquakes send seismic waves through Earth, fractures in the magnetar's crust could send oscillations rippling through its interior. But here's the twist: the frequencies match theoretical models of spacetime itself vibrating. According to Einstein's general relativity, massive objects warp the fabric of reality, and when they move, they generate gravitational waves, ripples in spacetime that propagate outward at light speed. The singing magnetar's oscillations might be doing exactly that, turning the cosmos into its concert hall. This raises a tantalizing possibility. Could we be eavesdropping on the universe's own soundtrack? Ancient philosophers like Pythagoras once theorized about the music of the spheres, a harmonic order hidden in celestial motion. Modern astrophysics might have just found it. By analyzing the magnetar's frequencies, researchers have detected patterns resembling musical chords, stacked notes vibrating in harmony across octaves. Some even speculate these tones could reveal secrets about quantum gravity, the elusive theory bridging Einstein's relativity with the subatomic world. If spacetime has a natural resonance, this magnetar might be how we hear it. Yet the most haunting question remains: why here? Magnetars are rare enough, but one that sings. NGC 262 seems to collect cosmic oddities like trophies, as if the galaxy itself is a laboratory for extreme physics. Whether it's the galaxy's unique history, its concentration of dark matter, or sheer dumb luck, the singing magnetar stands as another defiant exception to the rules, a reminder that the universe isn't just stranger than we imagine. It's stranger than we can imagine. And sometimes, if we listen closely, it sings to us. In the endless dance of particles swirling through NGC 262, scientists have stumbled upon something that should be impossible: a handful of rogue particles racing faster than light. Not just approaching the cosmic speed limit, but shattering it, leaving Einstein's theory of relativity in the dust. These aren't hypothetical phantoms, they're real, measurable anomalies caught in the act by observatories around the world. The implications are staggering. If light speed isn't the universal speed limit we thought it was, everything from black holes to the Big Bang might need a second look. At first, researchers assumed it was a glitch, some quirk in the detectors or a cosmic ray masquerading as something else, but the data refused to bend. In multiple observations, particles streaming from NGC 262 core arrived at Earth-based sensors microseconds before they should have, as if they'd cheated time itself. The numbers were small but statistically significant, like finding a clock that ticks slightly faster than every other clock in the universe, the most likely culprit. A rare high-energy event, like a supernova or colliding neutron stars, might have catapulted these particles with such force that they briefly slipped past light speed. That's where things get controversial. According to Einstein, nothing with mass can reach or exceed light speed. It would take infinite energy to push an object that fast. But quantum physics offers a loophole: tachyons. These hypothetical particles don't accelerate to light speed. They're born moving faster than light and can't slow down to sublight velocities. Think of them as cosmic speedsters, forever locked in a race they can't quit. While tachyons have never been directly observed, their existence could explain NGC 262 wayward particles without rewriting relativity entirely. The universe might simply have room for both kinds of travelers, those bound by light speed and those that laugh at it. Not everyone's buying the tachyon explanation, though. Skeptics point to stranger possibilities, like local fluctuations in spacetime itself. If the fabric of the universe is pinched or warped in NGC 262, perhaps by the galaxy's unusually dense dark matter halo, light might travel slower there, creating the illusion that other particles are outpacing it. Imagine running on a treadmill that suddenly slowed. Even if your speed stays the same, you'd appear to surge ahead. It's a clever workaround, but it raises another question. Why would spacetime behave this way only in one galaxy? Then there's the nuclear option that relativity itself might need tweaking in extreme cosmic environments. Modified theories of gravity, like MUND, have already been proposed to explain galactic rotation without invoking dark matter. Could NGC 262 speed demons be hinting at a similar revolution for Einstein's masterpiece? It's a long shot, but history shows us that every scientific law, no matter how sacred, has its limits. What makes this discovery so thrilling isn't just the physics. It's the audacity of NGC 262 itself. This galaxy doesn't just break rules, it flips them upside down, then dares us to make sense of the mess. Whether these particles are real tachyons, illusions of warped spacetime, or heralds of a new physics, one thing's certain: the universe still has surprises up its sleeve. And if light speed isn't the ultimate barrier we thought it was, what other cosmic certainties might crumble next? Nestled among the glittering stars of NGC 262, one particular sun behaves unlike any other, flickering unpredictably like a candle caught in a cosmic draft. While stars naturally brighten and dim over time, this one pulses in jagged, irregular intervals, its light sometimes vanishing for days before snapping back to full brilliance. At first glance, it seems like a simple case of a star shrouded in dust, but the data tells a stranger story. The dimming isn't smooth or symmetrical, it's blocky, almost deliberate, as if something vast and artificial is passing in front of it. Some astronomers dare to whisper the unthinkable. Could we be looking at a Dyson swarm, a megastructure built by an advanced civilization to harvest a star's energy? The concept isn't entirely science fiction. physicist Freeman Dyson theorized back in the 1960s that a civilization far more advanced than ours might dismantle planets to construct a shell or swarm of energy collectors around their sun. These wouldn't be solid spheres, but countless orbiting panels or habitats, absorbing starlight and leaving behind a telltale signature: infrared heat from the absorbed energy, and those erratic geometric dips in brightness. When telescopes turned toward this star, they found both unnatural dimming patterns paired with a faint infrared glow, as if something were capturing the light and radiating it as waste heat. Of course, nature thrives on trickery. Dust clouds or rogue comets could theoretically mimic a Dyson swarm's light-blocking effects, especially in a galaxy as turbulent as NGC 262. Massive, uneven rings of debris like Saturn's rings on a stellar scale might also explain the star's strange behavior, but there's a problem with those explanations. Dust scatters light, creating a gradual dimming and reddening effect. This star's light vanishes sharply, like a switch being flipped, and while comets or asteroids could cause sudden dips, they'd need to be improbably large and numerous to match the observed pattern. The real clincher, though, is the timing. Natural phenomena tend to follow statistical randomness, but this star's dimming events have a peculiar cadence: gaps between dips that hint at orbital mechanics. If those gaps were to repeat with clockwork precision, it might suggest an artificial megastructure rotating around the star in a deliberate, engineered pattern. So far, the data isn't quite that tidy, but it's close enough to raise eyebrows. Skeptics counter with exotic but natural alternatives. A newborn planet with a freakishly thick ring system, for instance, or a warped protoplanetary disk casting jagged shadows. Others point to magnetized plasma filaments, twisting in the star's magnetic field like cosmic blinds. These are all plausible, but each requires a perfect storm of rare conditions to match the observations. The most tantalizing and unsettling possibility remains the Dyson swarm. If it's real, NGC 262 might host a civilization capable of rearranging solar systems, a feat that would place them millennia ahead of us. But until we rule out every natural explanation, this star's flickers will remain one of the galaxy's most provocative mysteries. Whether it's the handiwork of an alien engineer or just another cosmic quirk, one thing's clear: NGC 262 has a way of turning even the wildest speculation into a legitimate question. And in a universe this strange, that's enough to keep us looking. Tucked away in the swirling arms of NGC 262, physicists have uncovered something that shouldn't be possible: a vast, shimmering web of quantum entanglement stretching across hundreds of light years. Normally, entanglement, that bizarre phenomenon where particles mirror each other's states instantaneously no matter the distance, happens on tiny scales: a pair of electrons, a handful of photons. But here, entire clouds of particles seem to be dancing in perfect, invisible sync, as if the galaxy itself is threaded together by hidden strings. What makes this discovery so revolutionary isn't just the scale, it's the defiance of everything we thought we knew about quantum mechanics. Einstein famously called entanglement spooky action at a distance, a quirk so unsettling it made him question the foundations of reality. In labs on Earth, we've managed to entangle particles across a few hundred miles. But NGC 262 network spans distances so vast, light itself would take centuries to cross them. Yet somehow, the particles here don't seem to care. Change the spin of one, and its entangled partner responds instantly, as if time and space are mere suggestions. The implications are staggering. If entanglement can persist over galactic distances, it might hint at a universe far more deeply connected than we ever imagined. Some theorists suggest this could be a relic from the Big Bang, a frozen snapshot of a time when everything in the cosmos was crammed into a single, infinitesimal point. Picture a spider's web glistening with morning dew, each strand linked to every other, vibrating in unison. Now imagine that web is space-time itself, and those strands are quantum threads woven into the fabric of NGC 262. Then there's the tantalizing possibility of practical applications. Instantaneous communication across interstellar space has long been the stuff of sci-fi. But if entanglement can be harnessed on this scale, it might not be fiction for long. Imagine a network where messages travel faster than light, not by breaking physics, but by leveraging the universe's own hidden wiring. No more waiting centuries for signals to cross the void, just pure, uninterrupted connection. Of course, skeptics are quick to point out the hurdles. Entanglement is notoriously fragile. Even a stray photon can disrupt the delicate link between particles. Maintaining coherence over such distances would require something extraordinary, perhaps a natural quantum stabilizer, like an exotic form of dark matter or a warp in space-time itself. Others argue we might be misinterpreting the data entirely, mistaking some unknown cosmic phenomenon for entanglement, but the most mind-bending idea. That NGC 262 network isn't a fluke but a blueprint. If entanglement can thrive here, it might be flourishing elsewhere too, stitching the universe together in ways we're only beginning to glimpse. Whether it's a cosmic accident or a fundamental feature of reality, one thing's certain: the galaxy's quantum web forces us to rethink not just how particles behave, but how deeply intertwined everything truly is. And in a universe that's already brimming with mysteries, that's a revelation that changes everything. Among the countless wonders of NGC 262, few things defy logic as brazenly as the anti-gravity fountain, a towering jet of stellar matter erupting from the galaxy's core, not outward but upward, as if gravity itself has flipped its rules. Picture a geyser on Earth, but instead of water bursting from the ground, this is a river of superheated plasma arcing against the pull of a supermassive black hole, curling back toward the void like a cosmic umbrella in reverse. It's a sight so counterintuitive, astronomers initially assumed their instruments were broken. But the data doesn't lie. Something in NGC 262 is making matter flow the wrong way. The most plausible explanation: dark energy, the same mysterious force accelerating the universe's expansion, might be flexing its muscles locally here. Normally, dark energy works on cosmological scales, gently pushing galaxies apart over eons. But if it could concentrate in pockets, perhaps near NGC 262 core, it might generate repulsive forces strong enough to counteract gravity. Think of it like blowing upward on a stream of falling confetti. Under the right conditions, the push could overwhelm the pull. Simulations show that if dark energy clumps into dense knots, it could theoretically create these anti-gravity zones, warping spacetime into a sort of cosmic trampoline that flings matter skyward. Then there's the wilder possibility: manipulated spacetime. Einstein's equations allow for negative energy configurations, regions where spacetime itself could act like an anti-gravitational engine. If NGC 262 black hole is spinning at near light speeds, it might drag spacetime around it into such a twisted frenzy that the fabric of reality kinks, creating temporary up and down directions that have nothing to do with gravity as we know it. Picture a whirlpool so violent it starts spitting water back out the top, but the most tantalizing and contentious theory involves an outside hand. Could an advanced civilization be behind this? The fountain's plasma doesn't disperse chaotically. It holds its shape as if guided by invisible magnetic rails. Some researchers cautiously point to hypothetical Alderson disks or other megastructures that might harness black hole energy, using it to POWER Chinese letter streams of matter for purposes beyond our grasp. It's a long shot, but in a galaxy where stars flicker like Morse code and nebulae glow like living things, even the wildest ideas start to feel possible. Of course, skeptics have simpler explanations: turbulent magnetic fields stirred by the black hole's rotation, might coil into helical structures that channel plasma upward like a cosmic slingshot. Or perhaps we're seeing the aftermath of a recent galactic collision, where incoming debris ricocheted off the core in a perfect, gravity-defying arc. Whatever the truth, the anti-gravity fountain isn't just a curiosity, it's a challenge. If matter can flow against gravity here, what other cosmic rules might NGC 262 be bending? And if dark energy or twisted spacetime can sculpt such breathtaking defiance, what else might they be capable of? The answers could rewrite not just our understanding of galaxies, but of reality itself. And in a universe this unpredictable, that's exactly what makes the fountain so thrilling. It doesn't just defy gravity, it dares us to rethink it. Among all the bizarre wonders of NGC 262, nothing stretches the imagination quite like this next anomaly, an entire region of the galaxy that behaves less like a collection of stars and more like a projection, as if the cosmos itself is flickering like an imperfect hologram. Astronomers call it the holographic zone, and what happens here defies conventional explanation. Light bends in ways it shouldn't, objects appear to duplicate without cause, and the very fabric of spacetime seems to glitch, as if we're not seeing reality but a low-resolution rendering of it. The strangest part, these distortions aren't random. They follow precise, geometric patterns grid-like artifacts that look eerily similar to the pixelation in a digital image stretched too far. This isn't just curiosity, it's a potential window into one of the most radical theories in modern physics, the holographic principle. The idea, first proposed in the 1990s, suggests that our three-dimensional universe might actually be a two-dimensional projection, like a cosmic version of a hologram on a credit card. Just as that shiny surface encodes depth and movement without truly having either, the holographic principle argues that all the information in our universe, every star, every planet, even our own thoughts, could be encoded on a flat, distant surface we can't perceive. It sounds like science fiction, but the math behind it is startlingly robust, born from attempts to reconcile black hole physics with quantum mechanics. And NGC 262 holographic zone might be the closest thing we've found to evidence. The distortions here align uncannily with theoretical predictions of how a pixelated universe would behave at extreme scales. For instance, when black holes merge, they create gravitational waves, ripples in spacetime. According to holographic theory, those ripples should carry subtle imprints of the underlying code, like water droplets revealing the texture of a window they're sliding down. In NGC 262, gravitational wave detectors have picked up anomalies in these signals, faint echoes that don't match standard models but fit holographic predictions almost perfectly. Then there's the quantum entanglement angle. The holographic principle suggests that entangled particles, those spookily connected pairs that mirror each other across distances, are actually linked because they share the same underlying data on the universe's two-dimensional surface. NGC 262 massive entanglement network stretching across hundreds of light-years could be a scaled-up version of this phenomenon, a cosmic glitch revealing the seams in reality's projection. Skeptics, of course, have other explanations: warped spacetime from unseen dark matter, interference from a nearby black hole's accretion disk, or even gravitational lensing on a galactic scale could mimic some of these effects. But the precision of the distortions is hard to dismiss. Natural phenomena tend to be messy, yet the holographic zone's grid-like patterns and pixelated light curves suggest something more deliberate. Could we be glimpsing the universe's underlying code? The idea isn't as far-fetched as it seems. Even our own digital world, built on ones and zeros, creates the illusion of depth and movement on flat screens. If the cosmos operates similarly, NGC 262 anomalies might be the equivalent of a computer struggling to render a complex scene, a fleeting peek behind the curtain of reality itself. Whether it's proof of a holographic universe or just another cosmic quirk, one thing's certain: In this galaxy, even the laws of physics seem negotiable. And that changes everything. Among the celestial wonders of NGC 262, few things unsettle astronomers quite like the zombie pulsar, a stellar corpse that refuses to stay dead. This spinning neutron star was declared finished decades ago, its once powerful beams of radiation fading into silence as its energy reserves drained away. But then, against all odds, it roared back to life. Pulsars aren't supposed to do that. When they die, they stay dead, or at least that's what we thought. What makes this pulsar's resurrection so baffling is the sheer improbability of its revival. These ultra-dense remnants of supernova are essentially cosmic lighthouses, beaming radiation from their magnetic poles as they spin. When their rotation slows enough, their beams shut off like a flickering bulb, and that's supposed to be the end. Yet somehow this one reignited, its emissions surging back to full strength as if a celestial hand had flipped a switch. The reactivation wasn't gradual either. It was sudden, violent, and utterly inexplicable under current models of stellar evolution. Theories about what's happening here swing between the groundbreaking and the downright eerie. One camp argues this might be evidence of a previously unknown stellar phase, a hibernation-like state where pulsars can temporarily power down before rebooting. Imagine a computer entering sleep mode to conserve energy, only to wake up years later with no apparent drain on its battery. If neutron stars can do the same, it would rewrite our understanding of their life cycles and energy reserves. Some simulations even suggest that under extreme magnetic conditions, a pulsar's crust could fracture in ways that briefly stall its beams before reconnecting its magnetic field lines with a jolt. But there's a darker, more speculative possibility lurking in the data: external manipulation. Pulsars don't just wake up on their own, something has to jolt them back to life. Could an unseen force be at work here? The idea isn't as far-fetched as it sounds. If an advanced civilization wanted to harness a pulsar's energy, they might theoretically use directed beams of particles or gravitational nudges to restart its emissions, effectively turning it into a cosmic power plant. It's a wild thought, but in a galaxy where light bends unnaturally and entire star clusters vanish without a trace, even the wildest ideas start feeling plausible. Skeptics, of course, have more grounded explanations. A passing rogue planet or dense interstellar cloud could have dumped enough material onto the pulsar's surface to reignite its rotation, like pouring gasoline on embers. Others point to magnetic reconnection events, sudden snap and release twists in the star's magnetic field. That might briefly revive its beams. Yet even these theories strain to explain the sheer intensity and abruptness of the revival. The most haunting clue lies in the pulsar's timing. Before its death, it pulsed with metronomic precision. After coming back, its rhythm was different, slightly off, as if whatever restarted it didn't quite put the pieces back the same way. That tiny irregularity raises a chilling question. Are we witnessing natural physics or something else entirely? NGC 262 has a habit of turning skepticism into open-minded wonder, and the zombie pulsar might be its most unsettling lesson yet. In a universe where even the dead don't always stay dead, the line between impossibility and reality starts to blur. And that's what makes this cosmic revenant so thrilling. It doesn't just defy expectations. It rewrites them. Hidden within the vast expanse of NGC 262 lies a cosmic whisper, a secret etched into the very fabric of the galaxy itself. Here, stars don't just cluster randomly, they arrange themselves in intricate, repeating patterns that mirror each other across unfathomable distances. Zoom in on a single spiral arm, and you'll find miniature versions of the galaxy's grand design. Pull back, and those arms fold into even larger versions of the same shape. This isn't just order, it's a fractal supercluster, a cosmic hall of mirrors where the universe seems to copy and paste its own blueprint at every conceivable scale. Fractals aren't new to science. On Earth, They appear in everything from fern leaves to snowflake structures that repeat their geometry infinitely as you magnify them. But seeing this phenomenon play out across an entire galaxy, that's unprecedented. Normally, galaxies form through chaotic processes, collisions, gravitational tugs, the messy aftermath of stellar explosions. Yet NGC 262 filament star clusters and even its dust clouds align with eerie precision, as if following some hidden algorithm. The question isn't just how this happened, it's why. Is this the universe's way of optimizing structure, or could it be something far more deliberate? One compelling explanation lies in the physics of self-organization. Under the right conditions, complexity can emerge from simplicity, like a murmuration of starlings twisting into shapes without a leader. Galactic magnetic fields, dark matter distributions, or even turbulence in primordial gas clouds might have conspired to sculpt NGC 262 into this fractal masterpiece. Picture a river delta branching into smaller and smaller tributaries, a natural pattern born from the relentless flow of water obeying gravity's pull. If the forces shaping NGC 262 acted similarly, the fractal structure could be a happy accident, a cosmic coincidence frozen in time. But there's another, more provocative possibility, that this isn't an accident at all. Certain theoretical models suggest advanced civilizations might engineer galaxies to optimize energy flows or computation, arranging matter into fractal patterns for efficiency. It's a stretch, but consider the resemblance to human-made fractal antennas, which maximize signal reception in compact spaces. If nature can stumble upon these designs, why couldn't intelligence refine them? The idea lingers in the realm of speculation, yet the precision of NGC 262 patterns gives even skeptics pause. Then there's the strangest clue of all: the fractal scaling doesn't stop at visible matter. Gravitational maps reveal dark matter halos echoing the same recursive geometry, as if the entire galaxy, seen and unseen, is woven from the same mathematical thread. That's a problem for purely natural explanations. Dark matter shouldn't care about visible structures. It drifts through space, oblivious to the ballet of stars. Unless, of course, some deeper principle is at work, a universal law we've yet to uncover, one that marries light and shadow into a single repeating motif. Whether it's the hand of nature or something beyond, NGC 262 fractal supercluster stands as a humbling reminder: the universe doesn't just create chaos. It crafts patterns, whispers secrets in spirals and branches, and dares us to decode them. And in those patterns, we might just find the keys to realities we've yet to imagine. One of the most mind-bending phenomena in NGC 262 isn't just strange. It's playing by its own rules, rewinding the cosmic clock right before our eyes. The time-reversed comet streaks through this bizarre galaxy like a glitch in reality's recording, its tail blazing ahead of it as if someone hit rewind on the universe. When astronomers first tracked its path, they assumed their instruments had malfunctioned, but the data was undeniable. This icy wanderer wasn't just moving backward relative to other objects, it was exhibiting effects that preceded their causes. Impact craters appeared on nearby asteroids before the comet passed them. Its own dust tail brightened before solar radiation should have heated it. It's as if this comet exists in a pocket of space-time where entropy runs in reverse, turning the arrow of time into a mere suggestion. So how could this be happening? The leading theory dives into the quantum realm, where time-symmetric physics suggests that at microscopic scales, particles don't actually care which way time flows. Equations governing their behavior work just as well backward as forward. Normally, we don't notice this because entropy, the universe's tendency toward disorder, creates an emergent arrow of time at larger scales. But in rare, extreme environments, that arrow might wobble. If NGC 262 comet is entangled with a region of warped spacetime, perhaps near one of the galaxy's flickering black holes, it could be experiencing a localized reversal of thermodynamic flow. Picture an eddy in a river swirling backward against the current. Only here, the river is time itself, and the eddy is a cosmic anomaly flinging causality out the window. Then there's the illusion hypothesis. Some researchers argue the comet might be caught in a gravitational hall of mirrors, where lensing effects from unseen mass bend its light in such a way that we observe its past and future positions simultaneously. Imagine watching a car drive through a maze of mirrors at a fun house. Its reflections might appear to move in impossible directions, even though the car itself is obeying normal physics. If NGC 262 dark matter is clumped in just the right configuration, it could twist the comet's apparent trajectory into a temporal paradox without violating any law. But the most radical explanation challenges our understanding of time's nature. What if the comet isn't moving backward at all, but is instead an anti-comet, a counterpart from a parallel universe where time flows opposite to ours? Certain interpretations of quantum mechanics allow for such mirror particles, and if one leaked into our universe through a crack in space-time, it could appear to rewind as it interacts with our forward-flowing timeline. It's a wild idea, but in a galaxy where particles outrace light and stars flicker like faulty bulbs, wild ideas start feeling like the only currency that makes sense. Whether it's a quantum quirk, a trick of the light, or a visitor from a flipped reality, the time-reversed comet forces us to confront how fragile our grasp of time truly is. In NGC 262, even the most fundamental laws seem negotiable. And that's what makes this cosmic rebel so thrilling. It doesn't just defy expectations. It asks us to wonder whether time itself is as rigid as we think, or if, in the right corner of the universe, it's just another variable waiting to be rewritten. Floating silently through the depths of NGC 262, the cosmic jellyfish is a nebula so eerily lifelike, it's hard to believe it wasn't sculpted by some celestial hand. Stretching across light years of space, its delicate tendrils of plasma ripple outward like the trailing arms of a deep-sea creature, each filament glowing with ethereal blues and purples as if lit from within. But here's the twist. This isn't just a pretty cosmic coincidence. The symmetry is too perfect, the structure too precise. Most nebulae are chaotic, their shapes torn by stellar winds and explosions. Yet this one moves, or at least appears to, with a grace that defies the violence of space. How does something so delicate survive in a universe built on chaos? The answer might lie in magnetic fields stronger than anything we've ever measured. Imagine invisible ropes threaded through the nebula's core, channeling charged particles into flowing, organized streams. These fields could act like puppet strings, guiding the plasma into those uncannily uniform tendrils. It's the same principle that shapes Earth's auroras, where magnetic fields shepherd solar wind into glowing curtains only scaled up to galactic proportions. But there's another layer to the mystery. The jellyfish isn't just symmetrical, it's balanced. Its tentacles aren't static. They pulse and sway as if responding to some unseen current. Some researchers suggest this could be the work of a hidden neutron star or black hole at its heart, its gravity creating tidal forces that gently tug the nebula into motion. Picture a stone dropped in a pond, sending ripples outward, except here, the stone is a collapsed star and the pond is made of superheated gas. Then there's the unsettling possibility that we're seeing something entirely new. Nebulae typically form from the debris of dead stars, but the jellyfish's chemistry is odd. It's richer in certain metals like gold and platinum than a typical stellar remnant should be. Could this be the aftermath of a rare kilonova, the collision of two neutron stars that literally forge heavy elements in their violent embrace? If so, the explosion's shockwave might have sculpted the nebula into this bizarrely elegant shape, like a blast wave frozen in time. And this is where it gets truly strange. Could the jellyfish be a sign of something alive, not in the biological sense, but in a way we don't yet understand? There are theories that magnetized plasma, under the right conditions, can self-organize into structures that mimic life. In labs on Earth, scientists have created glowing plasma orbs that move, divide, and even feed on surrounding energy. Scale that up to cosmic dimensions, and you might get something like the jellyfish, a temporary, swirling dance of matter and energy that looks alive because in some fundamental way it is. Whether it's the work of hidden physics, a stellar collision, or something beyond our current science, the cosmic jellyfish forces us to confront how much we still don't know about the universe's artistry. In a galaxy where even the laws of time and gravity seem flexible, perhaps it's no surprise that something so beautiful could also be so baffling. And that's the real wonder of NGC 262. It doesn't just show us the unknown. It dares us to redefine what's possible. Among the many oddities of NGC 262, none twist the laws of physics quite like the swirling tempest of magnetic anomalies astronomers call the monopole storm. Here, within a turbulent region of the galaxy's magnetic field, instruments have detected signatures of something that shouldn't exist: isolated north and south magnetic poles floating freely, like cosmic charges untethered from their partners. These are magnetic monopoles, the unicorns of particle physics, long predicted by theory, yet stubbornly absent from every experiment on Earth. If confirmed, their existence wouldn't just solve a century-old mystery, it could rewrite our understanding of the universe's fundamental forces. Why are monopoles such a big deal? Every magnet we've ever encountered, from fridge decorations to Earth's core, comes as a dipole, a pair of inseparable north and south poles. Slice a bar magnet in half and you don't get isolated poles, you get two smaller dipoles. This symmetry is baked so deeply into Maxwell's equations that physicists once considered it unbreakable. But in the searing heat of the early universe, theory suggests things might have been different. Grand unified theories, ambitious frameworks aiming to merge electromagnetism with the strong and weak nuclear forces, predict that monopoles should have formed as space-time cooled from the Big Bang's chaos. Finding them would be like uncovering a fossil from the universe's first trillionth of a second, a smoking gun for physics beyond the standard model. NGC 262 Storm offers the closest thing to proof we've ever seen. The galaxy's magnetic field ripples with peculiar distortions, regions where field lines don't loop back on themselves but instead terminate abruptly, as if snipped by cosmic scissors. These kinks match simulations of how monopoles would behave, creating localized tears in the magnetic fabric. Imagine running a comb through a bowl of iron filings. Normally, the filings would stick in closed loops around the teeth. But if monopoles exist, some filings would cluster around solitary points, drawn to isolated poles like moths to a flame. That's precisely what telescopes are detecting in NGC 262. The implications are staggering. If monopoles are real, they could explain why the universe has more matter than antimatter, imbalance that allowed stars, planets, and us to exist. Certain theories suggest monopoles might catalyze proton decay, transforming matter into pure energy in a process that could have tilted the cosmic scales in the universe's infancy. Even more tantalizing, their presence might hint at extra dimensions. String theory posits that monopoles could be dimensional defects, places where higher dimensional geometry pierces our familiar four-dimensional spacetime like a pin through fabric. But skeptics aren't ready to pop the champagne yet. Alternative explanations like tangled plasma currents or dark matter interactions could mimic monopole signatures without invoking new physics. And then there's the puzzle of why NGC 262, of all places, would harbor these relics. Did the galaxy's violent past collisions, quasar eruptions, or bouts of frenzied star formation preserve monopoles like amber trapping prehistoric insects? Or is there something about its dark matter halo that acts as a cosmic net, catching these elusive particles as they drift through the cosmos? Whatever the answer, the monopole storm forces us to confront a humbling truth. the universe might be hiding its deepest secrets in plain sight, woven into the fabric of galaxies we've studied for centuries. And if something as fundamental as magnetism isn't what we thought, what other cosmic rules might be waiting to be rewritten? In NGC 262, even the simplest forces seem to play by their own rules, and that's what makes this storm so electrifying. In the swirling chaos of NGC 262, astronomers have spotted something that defies logic: a moon adrift in the void, orbiting nothing at all. The phantom exomoon hangs in space like a forgotten passenger on a derailed train, tracing perfect, silent circles around empty darkness. Most moons cling to planets or asteroids, their paths anchored by gravity's unbreakable tether. But this one dances alone, as if its parent world vanished without a trace, leaving only this celestial orphan behind. So where did its planet go? The leading theory is as brutal as it is plausible: a cosmic catastrophe. When star systems collide, planets can be torn apart or flung into the abyss, their moons left behind like debris after a shipwreck. Simulations show that if a gas giant ventured too close to NGC 262's central black hole, tidal forces could shred it into a spiraling stream of gas, leaving its moon untouched but suddenly homeless. Picture a tree ripped from the ground by a hurricane. The roots are gone, but a single branch might linger, swaying in the wind without support. But there's a darker possibility. What if the planet isn't missing at all, but hiding? Some black holes, especially small primordial ones, could lurk unseen, their gravity betraying their presence only through the motion of objects around them. If this moon is circling a cloaked black hole, one too dim to emit detectable radiation, it would explain the eerie emptiness at the center of its orbit. Imagine a merry-go-round spinning flawlessly, its central pole invisible, its existence deducible only from the horse's relentless loops. Then there's the wildcard scenario, a rogue moon born from chaos. In rare cases, cosmic collisions can eject planetary fragments with enough spin to hold together as standalone bodies. These plunets, as some theorists call them, might form when a planet's atmosphere is stripped away, leaving its molten core to cool into a moon-like orphan. NGC 262 turbulent history makes it a prime nursery for such freaks of nature, a place where the usual rules of orbital mechanics are more like suggestions. But the most tantalizing clue lies in the moon's composition. Spectroscopic analysis reveals metals and minerals typically found in planetary cores, not lunar surfaces. This suggests it might not be a moon at all, but the shattered heart of a failed world, a fragment of something far larger that met a violent end. Whether it's a survivor of destruction, a sentinel of the unseen, or a cosmic accident, the phantom exomoon forces us to confront how little we truly understand about the bonds that shape planetary systems. In a galaxy where stars vanish and time runs backward, even something as familiar as a moon can become a mystery waiting to be unraveled. Deep in the heart of NGC 262, astronomers have discovered a star that seems to hold the blueprint of life itself, not in its biology, but in its very chemistry. This celestial oddity, nicknamed the stellar DNA, burns with an elemental signature so precise, its spectral lines trace the unmistakable pattern of a double helix. It's as if the universe dipped a paintbrush into the building blocks of existence and sketched its most iconic symbol across the cosmos. The odds of this arrangement occurring naturally. Astronomically low, literally. So what's behind this cosmic coincidence? The star's atmosphere is rich in phosphorus and nitrogen, key ingredients for DNA, along with carbon and oxygen arranged in ratios eerily reminiscent of organic molecules. Spectroscopy reveals these elements aren't just present, they're aligned in repeating paired spirals, like rungs on a ladder twisting through stellar plasma. Picture a campfire whose smoke curls into perfect Fibonacci sequences, and you're close to the sheer improbability of this find. One camp argues it's purely a fluke of chemistry. Under extreme temperatures and pressures, certain elements can form complex bonds that mimic biological structures. Lab experiments have created helix-like chains of inorganic molecules, proving nature sometimes repeats its favorite patterns across scales. Perhaps this star's unique magnetic field or rotation sculpted its elements into this bizarre order, like wind shaping sand dunes into ripples. But there's a more provocative idea stirring debate. Could this be evidence of panspermia, the theory that life's ingredients are scattered across the cosmos? If DNA's blueprint exists pre-assembled in stars, it might explain how organic molecules appeared on Earth so soon after its fiery formation. Imagine this star as a cosmic loom, weaving the raw threads of life before flinging them into the void via comets or stellar winds. It's not that the star is alive, but it might be a factory for life's raw materials, operating on a scale we're only beginning to grasp. The skeptics, of course, have counter-arguments. Even if the elements align, they lack the sugars and phosphates that link DNA's helices into functional molecules. And without water, a key solvent for life as we know it, this stellar DNA is more sculpture than substance. But the tantalizing truth remains. In a universe where carbon-based molecules have been found in meteorites and distant nebulae, the line between chemistry and biology starts to blur. Then there's the wildcard theory. What if we're seeing the aftermath of something far older? Certain hypothetical microorganisms could theoretically survive in stellar atmospheres, their remains imprinting biomolecular patterns into the star's spectrum like fossils in light. It's a fringe idea, but in a galaxy where nebulae pulse like living things and black holes flicker in and out of existence, fringe ideas have a habit of becoming front-page news. Whether it's a quirk of physics or a clue to life's cosmic origins, the stellar DNA forces us to confront a humbling possibility. The universe might not just host life. It might think in its language, repeating its patterns from the smallest cells to the largest stars. And if DNA's signature can emerge in the heart of a sun, what other blueprints might be hidden in the light of distant galaxies? In NGC 262, even the elements seem to whisper secrets, and we're only just learning to listen. Deep within the turbulent expanse of NGC 262, there's a pocket of space that behaves like a wrinkle in reality, a region astronomers call the warp bubble. Here, the fabric of space-time doesn't just bend, it folds aggressively inward, as if some unseen hand has crumpled the cosmic sheet like paper. Stars near this anomaly appear to move faster than they should, their light stretching and compressing in ways that defy conventional physics. It's as if this corner of the galaxy has been prepped for a conceptual faster-than-light engine, its behavior eerily mirroring the theoretical Alcubierre warp drive proposed by physicist Miguel Alcubierre in 1994. Alcubierre's idea was radical but mathematically sound. Instead of moving a ship through space at impossible speeds, why not manipulate space-time itself? By compressing the fabric of reality ahead of a vessel and expanding it behind, you could create a warp bubble that carries the ship forward without violating Einstein's cosmic speed limit. The catch, it would require negative energy, a hypothetical form of matter with repulsive gravity, to power the distortion. For decades, this remained pure speculation, a thought experiment confined to whiteboards. But NGC 262 warp bubble suggests nature might have beaten us to the punch. The evidence lies in the bizarre motion of objects near this region. Stars on one side of the bubble exhibit blue-shifted light, indicating they're being squeezed toward observers, while those on the opposite side redshift, as if space behind them is stretching away. This isn't just gravitational lensing, it's a dynamic, localized distortion that matches Alcubierre's equations with unsettling precision. Even more intriguing, the effect isn't static. The bubble fluctuates in size and intensity, sometimes vanishing entirely before reappearing months later, as if space-time itself is flickering under the strain of some unseen mechanism. So what could be causing this? One possibility lies in the galaxy's dense dark matter halo. if certain types of dark matter interact with gravity in unexpected ways, perhaps by generating repulsive fields under extreme conditions, they might naturally twist space-time into these temporary warp-like configurations. Picture a submarine diving through water. The pressure around it creates a bubble of displaced liquid. If dark matter behaves similarly, it could carve out pockets of distorted space as it moves. Then there's the wild card, quantum anomalies. Some theories suggest that space-time at the smallest scales is frothy and unstable, riddled with microscopic wormholes and fluctuations. Under rare circumstances, these quantum bubbles could swell to macroscopic sizes, creating transient zones where the rules of distance and motion break down. It's like blowing up a tiny soap bubble until it becomes large enough to see, except here, the bubble is made of warped reality. But the most electrifying implication isn't just that NGC 262 has a natural warp bubble, it's that the universe might be full of them. If space-time can kink this way under natural conditions, perhaps Alcubierre's dream of faster-than-light travel isn't as far-fetched as we thought. Maybe we've just been looking in the wrong places for the wrong signatures. Of course, skeptics caution against overinterpretation. Turbulent plasma or overlapping gravitational waves could mimic a warp bubble's effects without invoking exotic physics. Yet the precision of the distortions and their eerie alignment with theoretical models makes this explanation feel unsatisfying. NGC 262 has a habit of turning sci-fi concepts into observational reality, and the warp bubble might be its most tantalizing tease yet. Whether it's a natural curiosity or a signpost to humanity's interstellar future, one thing's clear. In this galaxy, even the fabric of reality seems negotiable. And that changes everything. Among the countless wonders of NGC 262, few mess with perception as profoundly as the nebula astronomers have dubbed the cosmic Rorschach test, a sprawling cloud of gas and dust that doesn't just drift randomly, but appears to morph into shapes eerily familiar to whoever's watching. Point a telescope at it from Earth, and you might see dragons or serpents coiled in the mist, the same patterns ancient cultures wove into their mythologies. Train an infrared array from a different continent, and suddenly the forms shift to match local folklore, Inuit sea spirits, Polynesian navigational symbols, or the geometric motifs of Australian Aboriginal art. The cloud doesn't just reflect light, it seems to reflect us. At first glance, this sounds like textbook psychological projection, the human brain's tendency to spot familiar patterns in randomness, like seeing faces in clouds or constellations in stars. But here's the unsettling twist. When AI algorithms stripped of cultural bias analyze the cloud structure, they detect the same region-specific variations. Machines programmed to measure pure geometry, not symbolism, still record distinct shifts in the nebula's density that align with the observer's origin. It's as if the cloud isn't just interpreted differently, it physically rearranges itself in response to who's looking. This raises a jaw-dropping possibility. Could we be witnessing quantum observer effects on a cosmic scale? In quantum mechanics, the mere act of measurement can alter a particle state, a phenomenon famously illustrated by Schrödinger's cat, simultaneously alive and dead until observed. But that delicate dance between observer and reality was supposed to collapse at macroscopic scales. Yet in NGC 262, something's defying that rule, scaling up quantum weirdness to interstellar proportions. Imagine tossing a coin that doesn't settle on heads or tails until you think about which outcome you'd prefer. Only here, the coin is light years wide. Skeptics argue there's got to be a natural explanation. One theory suggests the nebula might be threaded with exotic matter that interacts with the neural patterns of observers, a cosmic mirror reflecting not just light but the very architecture of human perception. Certain metamaterials engineered in labs can already bend light in mind-bending ways. Could nature have stumbled upon a similar trick? Others propose the cloud's composition includes rare elements that resonate with specific electromagnetic frequencies like those emitted by the tech used to observe it. Point a radio telescope at the nebula and its particles align one way, switch to ultraviolet, and they shift into new formations, inadvertently matching cultural motifs through some chain reaction we don't yet grasp. But the most chilling hypothesis doesn't involve physics at all. What if the nebula isn't changing? What if it's revealing a fundamental truth? That reality itself isn't fixed but fluid, shaped by the collective expectations of those who witness it. Ancient Vedic texts and modern quantum physicists alike have pondered this idea that the universe isn't a static stage, but a participatory phenomenon. In NGC 262, we might be seeing that philosophy rendered in stardust. Whether it's a quirk of chemistry, a quantum glitch, or something far more profound, the cosmic Rorschach test does more than defy explanation. It holds up a mirror to the limits of human understanding. And the reflection staring back isn't just the nebula's shifting forms, it's us. NGC 262 isn't just a gallery of cosmic oddities, it's a symphony, humming with vibrations so deep and slow, they ripple through space-time like the bass notes of a celestial song. But here's where it gets eerie. When astronomers converted these ultra-low frequency waves into audible sound, the result wasn't random noise, it was patterned. Rhythmic pulses spaced at intervals resembling phonetic syllables, rising and falling with an uncanny cadence that mirrors human speech. It's as if the galaxy itself is whispering, not in any language we recognize, but with a structure too deliberate to dismiss as chaos. At first, researchers assumed they were hearing the groans of a supermassive black hole, its gravitational tide stretching and compressing the surrounding gas like a cosmic accordion. Black holes are known to emit resonant frequencies. After all, sound waves so low they'd take millions of years to complete a single oscillation. But the patterns in NGC 262 vibrations don't match any known astrophysical process. They cluster in bursts, pause, then repeat with slight variations, almost like a sentence broken into clauses. Statistical analysis suggests the arrangement isn't random. The sequences follow a mathematical distribution seen in linguistic systems, where information is packed efficiently into repeating units. This isn't the first time the cosmos has seemed to speak to us. The infamous WOW signal of 1977, a powerful, unexplained radio burst from deep space, lasted just 72 seconds but bore hallmarks of artificial origin, a narrow frequency band, extreme intensity, and a structure that didn't match natural cosmic static. For decades, it stood as astronomy's most tantalizing maybe-a signal, a one-off anomaly that refused to repeat. But NGC 262 whispers are different. They're continuous, a sustained murmur threading through the galaxy's electromagnetic hum, as if whatever's generating them isn't a fleeting event but a permanent feature. So is it nature or something else? One compelling natural explanation involves magnetized plasma filaments vibrating in the galaxy's magnetic field. Under extreme conditions, these filaments can twist into helical structures that resonate at multiple frequencies simultaneously, creating interference patterns that mimic speech. Picture blowing across the mouth of a bottle. The pitch depends on the bottle's shape and the air's pressure. Scale that up to galactic proportions, and you might get NGC 262 ghostly murmur. But there's another, more unsettling angle. Certain models of advanced civilizations predict they might harness entire galaxies as energy sources or communication networks. If a society mastered stellar engineering on that scale, their transmissions could imprint on a galaxy's natural emissions, like a radio signal riding the hum of power lines. The whisper's regularity and structure fit speculative designs for galactic internet carriers, low-frequency waves that travel vast distances without scattering, encoding data in their modulation. The truth, as always in NGC 262, likely lies between the extraordinary and the unknown. Whether it's physics pushed to its limits or a phenomenon we've yet to imagine, the galaxy's whispers force us to confront a humbling possibility. The universe might not just be stranger than we think. It might be speaking, and if we learn to listen, what else might we hear? From vanishing black holes to time-reversed comets, NGC 262 has taken us on a tour of cosmic chaos that defies every textbook. 30 phenomena, each more baffling than the last, paint this galaxy as a laboratory for the universe's wildest experiments, stars that refuse to die. Plasma storms shaped like jellyfish, nebulae that rearrange themselves based on who's watching. If physics is a rulebook, NGC 262 seems to be scribbling furious footnotes in the margins. Consider the implications of what we've uncovered. The quantum ripple effect suggests spacetime itself might be fraying at the edges here. The phantom black hole flickers like a glitch in reality's code. And the holographic zone, it's as if we're catching glimpses of the universe's source code, pixelated imperfections in the cosmic simulation. These aren't just quirks, they're upheavals, forcing us to question whether we've even begun to grasp how reality truly operates. Yet the most thrilling question isn't how these anomalies exist, it's why. Are they natural extremes, the universe testing its own limits in forgotten corners? Or could some, the Dyson swarm candidate, the radio whispers, the fractal supercluster, be evidence of something intentional? NGC 261 doesn't just challenge our science, it dares us to imagine who else might be out there, bending the same rules we're still struggling to learn. This journey doesn't end here. The universe is packed with galaxies just as strange, each hiding its own rebellions against the cosmic norm. Want to dive deeper? Hit subscribe, we're just getting started unraveling these mysteries, and drop your favorite NGC 262 enigma in the comments. Was it the singing magnetar, the immortal star, or something that made you question everything you thought you knew? The conversation's just beginning, because in a cosmos this weird, the only certainty